basic rules of line diagrams. I'm going to look at the function of line diagrams. We're going to get into logic. Some of the first labs we're going to wire up. The first lab we're going to do is we're going to wire transformer. We're going to learn how to wire the transformer. It's a dual voltage transformer. And we'll see how to wire it for high voltage and wire it for low voltage. The first two labs you're going to do are at-home labs. And they'll be due next Tuesday once we get over and give you all the procedure for the labs and all that other kind of stuff. But I think one of them is safety and one of them is lockout, tag out. You know. One of them deals with like current levels and that kind of stuff. I can't remember exactly which ones that are. It's inside the first chapter. Okay, so these are some of our rules. No more than one line per, no more than one load per line. No more than one load per line. Y'all understand that? Why would we have a problem? Well, these devices are rated at 120 volts. This right here would be a series circuit. When you set up a series circuit, then the voltage is distributed across the loads depending on their opposition. So that means, and voltage varies with the, power varies with the square of the voltage. Y'all understand why? Okay. So V is equal to I times R. So if I've got a certain amount of resistance, let's say I got 100 ohms, and my voltage is equal to 100 volts. But the problem is I is equal to, let's start it off different. So let's do 10 volts, and then what we'll do is we'll double. So let's say my V is equal, so I'm going to say I is equal to V over R. So let's say I have 10 ohms, and I have 10 volts. Well, then I would be equal to 10 divided by 10, and that's going to equal to 1, right? 1 amp. Okay. So up here when I say P is equal to V times I, then P would be equal to 10 times 10. That is going to be, 10 times 1. We solve for I, not R. 10 times 1, so there's my volt. So my power would be equal to 10 watts. Everybody follow that so far? So let's say I come up and I double my voltage. I'm not going to change my resistance, right? You'll see that. So I'm going to come up here and double my voltage. So we go to 20 volts. Okay. So now I is going to be equal to V over R. So I is going to be equal to 20 divided by 10. Which is going to give me 2 amps. Now power is equal to V times I. So when I look at my second one, this is going to be 20 times 2. So now we have 40 watts. So when I double the voltage, what happened to the power? It went up 2 squared. So power varies with the square of the voltage. So that means if I've got a relay that's designed to run off 120 volts, and it's got to have a certain amount of watts, right, to work, and I drop that down to 60 volts, that relay is not going to pull in anymore. It's not going to have enough energy to pull in because I half the voltage. So if it goes down, it's 1 over the square. If it goes up, it's times the square, right? Because if you half the voltage, you half the current. If you double the voltage, you double the current. So power varies with the square of the voltage. So that means if I hook these suckers in series, they're not going to work. The light bulb will be on, but you won't even be able to see it anymore because it's developing 1/4 of its power. Well, it depends on the resistance. Your relay is not, your solenoid's not going to pull in because why? It's designed around 120 volts. It's designed to give me the amount of work at 120 volts, and I drop that voltage down. And it does not vary with the voltage. It varies with the square of the voltage. So we do not put loads in series. And we call this a line. So this is a line. Now what we can do is we can hook them in parallel. These are different lines. A line is something that moves horizontal, like this. It don't have to go all the way to L2. All it's got to do is move horizontal. This is a different line. So every load has to have its own line. It don't have to have its own rung, but it's got to have its own line. So they're all part of the same rung, but they're different lines. And if you're taking the PLCs, this is the big difference in that we number lines. We don't number rungs. In PLC, we number rungs. In motor controls, we number lines. So this rung would consist of 2 lines. And what we do over here on the left, we put line numbers. And of course, they could start anywhere, but right now we'll start them with the number 1. So this would be line 1, that would be line 2. So in motor controls, we don't number rungs, we number lines. In PLCs, if you take PLCs, you'll number rungs. And so a line could have a rung could have multiple lines, and it does. Now this is legal. This is not. This is bad. Good, bad, good, bad, good, bad, good. But I could keep adding devices, so I could come down here and I could drop down here and I could put a relay coil. Make sure I put a dot, because if I don't put a dot, I don't have a line. Okay. And then I could give it a number, or a name. And I could keep doing it and doing it and doing it and doing it, right? You understand that? So as long as you don't exceed the rating of your power source, so your power source is going to be able to provide a certain amount of watts or a certain current at a certain voltage. If you exceed your power source, then you got a problem. As long as you don't exceed your power source, we can put as many lines inside a rung that we need, right? But what I would do out here on the left is I would put another number indicating I had another line. So this is legal. Control relays, solenoids, and pilot lights are loads that are connected directly or indirectly to L2. Very seldom. The only thing, and I think we ought to get rid of that indirectly, because if it's not, the only thing that's allowed to have something over here on L2 is the motor starter. And we'll have our overloads over here. Besides that, all your loads are going to be connected. Now the load is the part of the circuit that does the work, right? You understand that? So normally when we talk about, we can connect things in series, but it's not going to be a series circuit. When we start talking about series circuits, we're talking about how the loads are connected. Here in the control, we have no series circuits. We can hook control devices in series, but it's still not a series circuit. You'll understand the difference. So when we start talking about a series and parallel circuit, we're talking about how we connect the loads. So this would be a parallel circuit. even though that switch is in series, it's not a series parallel circuit, right? You understand? Are we okay? What's your name? What's your name?
West.
Yes. Yeah. Any reason why you couldn't get back in 10 minutes? What's going on? Right. David, you Wayne, my problems out there?
It was 4:12, it wasn't before. I got back 2 minutes before. It's just 12 o'clock. It might have been 12:01. It's not 11 yet.
Oh, okay. Then I
I
just,
ran down and got a snack.
okay.
So I didn't want to eat something.
Don't need public class. No, we don't need class, right? So we okay here? Who left? Well, somebody's sitting on the back table. Who is back there? So y'all did fine. It was my mistake. I started class up early. So. So this is true. The only thing that's allowed between L2 and the load is overload. Negative motor starter coils are connected directly to L2 through a normally closed overload contact. And this is the only thing that we're allowed to draw between the load and L2. Anybody know why? Yeah, what we're trying to do is we're trying to move power from everything over here. Okay, understand? So if I come up here and open up that switch, and then I get between hot and here, then it's still going to be literally hot, right? Well, not hot. It's still going to have voltage through this thing up here. If we open up here, then if I get between here and there, then it's not going to cause any problem because it's over. So the overload is the only thing that's allowed to go on the L2 side of the load. And what does an overload do?
It opens when it's supposed to. Too much current for a long period of time.
Yeah, but these guys are designed to protect motors. And what they do, we have a sensor in the motor circuit. This is not the sensor. This is the contact being controlled by that sensor. And what the sensor is looking at is it's looking at overcurrent over time. Does that terminology mean something? So we don't see the actual overloaded sensor itself. That will be in the power circuit. And we have two diagrams. We have the control diagram and then we have the power diagram, right? The control diagram is usually a ladder diagram, and then the power diagram is going to be part of your wiring diagram. So later on, when you get wiring up motors, you're going to have to understand how both of them work. Control devices. Control devices are connected between L1 and the load. How many control devices can we have per line? I want to say a bunch. Yeah, they don't do any electrical work. So they don't, you don't understand, they don't do work. They either turn that voltage on or they turn the voltage off. So they do know, they have a function, but they do work. They don't do work. When we talk about work in this class, we're talking about watts or VA. They don't produce VA. So here's a symbol for a push button, normally open push button, and unfortunately the book draws those things really close together. Then we have a normally open limit switch, and then we have a normally open pressure switch. So there's a new symbol for pressure switch. So the pressure switch kind of looks like a float switch, but it's a hassle. And we pass the limit switch around. I don't have a pressure switch in here. We got a sensor for a pressure switch, but we don't have the switch on it. We can hook these devices in series. It's not a series circuit, but we can hook them in series or we can hook them in parallel. This is still only one run, but now we have multiple lines. So what's nice about our control devices, we can hook those in series or we can hook them in parallel, depending on what we want the control device to be. Pick up two new symbols up at the top. What's the first one on the left? Flow switch. This tells us how fast a fluid is moving, right? Well, they don't tell us how fast. This switch just tells us if the fluid is moving or it's not moving. I have my HVAC system uses gas heat, and the problem with natural gas, it likes to blow up. So what they do before they arc that, so it's got a little spark plug in there called igniter that lights the main gas flow, but you don't want to light that thing if there's any gas inside that gas chamber. So what they do is they turn on the fan that purges the gas chamber, purges the chamber before they turn on the main gas, before they turn on that arc. Well, it's got a little flow switch in it. So if that thing don't come on, if they don't sense flow of that air, that fan's blowing through that combustion chamber, then they don't allow the main gas to turn on, and they won't turn on the igniter because they don't know for sure that there's no gas in that chamber, right? So, but all it's trying to do is sense whether that fan comes on or comes off. So when it turns on, it blows a flow, and it has a little vein in there. So all it is when it blows, it does what? Pushes that little vein up, and it lets the igniter turn on. But what we're doing here, to energize this relay right here, that magnetic motor starter right there, what do we have to do? The flow switch has to be closed, and the temperature switch has to be closed. You hear what I said? What did I say? And, but I use the term and. Now this is and logic, right? And means everybody, right? All. Even if you say all, or if you say both, of course, we'll say both if we have two devices that are connected in an and operation. But I should say if I go to three, then both don't come into play. But if I use the term all, if I say all of them have to be closed, then that's an and operation. That's logical. That's logic. But what about the second one? We got a flip switch and we got a pressure switch. Yeah. Now here, the flip switch can be closed, or the pressure switch can be closed, or any. If we use the term any, that's an or. That's a logical. And we only have three in the motor controls. We have ands. No, I'm sorry. We got nors. We got five. We got ands, ors, nots, nans, and nors. And we'll learn how to identify those ways that we can hook control devices. So when we can hook control devices an and, we can hook them in or, we can hook them in a not, a nan, and a nor. Or we can hook them in combinations. So I can have a not and a nan. It's really neat. We had a PLC here, one of the first ones that came out, one of the first fixed PLCs programmed in ands or. So you'd have to say, I want to and this contact with that contact, I want to or it. And now we draw them. So line numbers. So every horizontal conductor has a line number. And we put the line numbers on the left of L1. So when I go back to this big old US Steel print, which is a true print, it's a true ladder diagram. Oh, it's in the, I need to pull it into here. Dang. We could see all those line numbers. ETC, motor controls, graphics. No, that's not the one I want. And that one don't want to load. Oh, let me go to handouts. So this is one from US Steel. And you see all these numbers on the left of what they're calling it PO1, PCO1. All these are line numbers. Now on theirs, we have two things. We have a page number followed by a line number. So this is 13701. So that's line number 1 right there. Now this guy right here is line what? 2. Now if I come over here, if I move imaginary line from this line to that line, they line up perfectly with each other. So those have the same line number. So what we're talking about, if I take an imaginary line and so if I take an imaginary line and I move it from here over to there, those are the same line. You see that? Okay. Notice when I come over here and go over that, these are all the same lines. Now this guy right here gets his own number, or this guy right here gets on this number. So notice each one, when I draw a horizontal line from side to side, it lines up with a number over here on the left. Now US Steel uses page numbers, so these are all lines on page number 137. So that way when you turn to line number 138, they can start using 1 again, right? Because it'd be 138, because if they didn't do it that way, you're talking about, I don't know how many lines were in these diagrams to run this mill, but there was thousands of lines. But every time they turn the page, the line number becomes what? 138, and then they start using 01 again. So, and that's the technique, but it's still the same standard. You'll see that? Y'all understand that? Make sense? So I'll leave this up. In fact, I'll make it full screen. And there's a copy of this, by the way, available. And you're going to have to learn how this works. In fact, toward the end of the semester, the test, there's going to be questions on the test concerning this, because when we give it in the book, we give it generically, so we make it a little easier, right, to understand that. But when you get into it, it's the same thing. It's just they're going to have to add more information to these things because they're so dang big, right? Understand? By the way, these are disconnects up here. So this is the main power that feeds all the line diagrams. And then this right here becomes our L1 and L2 right here. And you're going to have to do this on the lab. This is at home lab too. It always amazes me. You have no questions in class, and then you have to do it on your own, and you have no idea how to do it. But you don't ask questions in class. Okay. Now look on the right-hand side of L2. The location of normally open contacts controlled by devices are determined by the number on the right side of the line diagram. Now, look, so up here, CR1, I look over here on the right, they've got it in parentheses. It might not necessarily be in parentheses, but they got the number 2, 3, and 4. And this gives this class the more problems that Now notice line 3. So now I can talk to you, right? So I can say, okay, everybody look at line number 9. So instead of me trying to say, okay, go from the 3rd line to the top, the 4th line to the bottom, I can give you a what? A number. And you know exactly, when you go over on the left-hand side, you find that number. Okay. Now notice on L3, that's the symbol for a lamp, right? You understand? And there's nothing on the right-hand side of L2 because a lamp has no contacts. So only the devices that have contacts, only relays will have numbers on the right-hand side of L2. Solenoids won't have numbers because they have no contacts, right? You understand? Can y'all see what the numbers are telling us? So up there in line number 1, I look out past CR, it's a relay. That's a symbol for relay. So what's going to happen is we have people throw all types of numbers over here. And of course I just mark them up. Because they don't have an idea. They'll put numbers out by light bulbs. They'll put numbers all over the place. And they think I'm looking for numbers. So I'm grading to make sure you are. But CR has contacts. Well, look at the first thing it says. So the name of that relay is CR1. Every contact that is controlled by that relay should have a label above it called CR1. Okay. So I look at line 2. And when I look in line 2, I see a contact label what? CR1. Then I come up here and it says line 3. Well, I go down here and look at line 3. I see a contact in line 3 labeled what? CR1. I come up here and look at line 4. I go up and look at line 4. There it is. We don't see this normally, but even if we break L1 and L2, it gets a wire number. And there it is right there. I come down here and look at I look at the light bulb. Why aren't there any numbers on the right-hand side of L2 or a light bulb? It has no contacts. Thank you, Nicholas. Hopefully you're not the one that put numbers out there. Now, I come down here and look here. Here's CR2, and it says line what? 8. I come and start following line 8 over, and there it is. There's a contact belongs to CR2. It says I've got one in line 10. I find there it is right there. Okay, I'm through with that. So now I know I don't have to look for any other contacts because it tells me where these contacts are at, right? You understand? I come up here and look at CR3. It says I have a contact in line 7. Look at line 7. There it is. It says I have a contact in line 9. There it is. It says I have a contact in line 11, and there it is. So I go back here and look at my US Steel print. Even though it's a lot more complicated, there's my line numbers right there. So I know that this relay right here, this 5B1DB, has a contact in line number 137-2. I come over here and look at 137-2, start following it over. Now, I didn't see it right there, so I'm going to move over here, and there it is right there. 5B1DB right there. That's the contact that belongs to that relay. And notice it even goes off page. I mean, there's some lines that point us out to a different page number. This guy here has a contact on page number 74, or line 74-66. Well, 74 is indicating the page number of the prints, right? You understand? And then I would find line number 66, and I would follow it over, and I should find the name of that same name right there. Now, this is US Steel. This is the textbook. Okay. Now, what we do is we differentiate between normally opened and normally closed contacts. Okay. So notice this diagram has some normally closed contacts and it has some normally open contacts. By the way, normally we don't draw the loads over here. Usually the loads are lined up. And why do we line them up? To make them real easy to see, right? So normally they don't ship the loads over here, even though they're nothing but light loads. I think they shifted it over so they have enough room to put their little comment in there. Now, so what we've done is we've added to the previous line diagram. Up there on line 1, I see 2, 3, 4, nothing on line 3. On line 5, I see 8, 9, 12. On line 6, I see 7, 10, 11, 13. I get down to line 8, I see a relay, but there's no contact numbers on there. What's going on there? It's a relay. It's a relay. Relay has contact. Nobody can take a guess. Yeah, right here. I come down here and I hit this relay. So there's a relay right there. In fact, it's a motor starter. How do I know it's a motor starter? It's got overloads out there. So this is a motor starter. Now, the motor starters that don't have overloads are a little harder to detect. But by George, if you see an overload symbol, that means that sucker right there is a motor starter. But when I come out here and look, it's right there. There's no contact. There's no line numbers listed. This is the control diagram. That's exactly right. Somewhere I'm going to have a diagram that has this. That has my motor, if it's a 3-phase motor. And this is going to be labeled M1, M2, and M1, M1, M1. So the power circuit is not, this is not the power, this is the control. So that guy has no auxiliary contacts on it. So if it does not have a contact within the control circuit, there's not going to be any numbers out there. But it will have contacts within the power diagram, right? You understand? Good catch. Now look at number 9. Then I come up here and I see this number right here. So this guy here got a contact somewhere within my control diagram. Sometime within my control diagram. That was a long one. But when I look at this, the number 12, what's the difference between this one and the rest of them? So there's number 12, and then I look up here. What's the difference? What's the difference between the 12 and all the numbers so far? It's underlined. Where's this in the book, by the way? So you have to be looking. This is right out of the book. 193. All the diagrams come out of the book, except for the US Steel one. And if you want to start studying that thing, I'll eventually give you a copy of it. But if you want to start looking at it, you can print that off. Because that is an actual true line diagram instead of one that's in a book, right? You understand what we're saying? Right out of US Steel. We called a class for US Steel. They had a self-paced, self-study course at US Steel. US Steel pays for tuitions for people to come to colleges. But it's almost impossible for them to do because they're on rotating shifts. But they had a group of employees go through a program up there with a self-paced, self-study. In fact, the Navy tried that for a while, where you come in, you sit in front of a computer, you take these lessons, you take those lessons, and you keep going until you pass them. You come in, and it's really neat because you could come in any day. They could put people in the class any day, and when they got through, they got through. US Steel tried that technique, and then they put them people up there for a year, and they come back, and there was nobody that passed the test. So they brought them out here for seemed like 2 weeks, and they paid them. There was 18 people in the classes. And we taught them, we tag taught because we had to teach our other classes. Me and Nancy and another guy called Paul Terry taught these classes and for 2 weeks. And then when they got out of that class, 16 people passed the test and did electronic voting. We had one guy that realized that he would be making less money if he got over his electronic voting because he was an operator. And the other one, we had one guy that failed it, but he passed it the second time. And then we had one lady that had to leave because she had to Refer to that. Because, so even the Navy has gone back to instructor-based teaching. I don't know about the other services, but yeah, it was real neat. But notice this has an underline, so let's look at it in line 12 and it's an into contact, right? So let's find that into contact, line 12, and follow it over. What's the difference between this contact and the other contacts that we looked at so far? Yeah, normally closed. So if it's a normally closed contact I'm looking for, we put a line under it. If it's a normally open contact we're looking for, it doesn't have a line. You understand that? So I'll go back and look at my U.S. Steel prints. And we'll zoom them up a little bit. Okay. And then we'll come over here. So right here it says, and of course, unfortunately, this print don't go all the way down to line 69. Let's see if we got one that goes down to. So here, 137.04, I'll be looking for a normally open contact in line 4. This is 137.63, which I don't have line 63, but we would be looking for what? Notice this one is what? Underlined, this one's not. So basically, not only does it tell you where the contacts are at, it gives you the name of the relay. So here's the names of the relay up here at the top. Now most of ours will put a little letter inside the symbol, but odds are when you get out on a true line diagram, they're not going to have enough. They got so many relays they can't just call them M1, M2, and 3. They got to give them relays bigger names, right? Understand? And then it tells me what line they're in, and then it tells me whether I'm looking for an open, closed, or normally open. And then what we do is, then every contact has a name above it. And what we're doing is we're looking for a name that matches the relay name that we're trying to find. That makes sense? So now we can talk, now we can find contacts. So instead of me trying to look over all these diagrams, trying to find the contacts that belong to that relay, because where can those contacts be at? They'll be anywhere, right? You understand? Inside the control diagram, it gives me a method that I can find those things real quick. These were 4.5D prints too that we had. This is drawn down a little over time frame, which is pretty neat. And there was a book, that sucker was about that thick. Because this was the prints on a manufactured line, a big application. And if they don't give you some way to find things and find it real fast, then you could be there. Like I said, this is page 137, so that means that there was 136 pages past this, and the biggest page number this right here references is 141. So there's a reference to a page 141 right there. And this was just one section of the line. They had what they called a feeder end, then they had a processing end, and then they had an exit end. And every one of them had their own set of diagrams. I don't know what this was. What I like about these is they give you the names of the relays and what they stand for over here on the left. So number 5 bridle, number 1 dynamic braking contactor. Which don't mean anything, but we'll talk about some of these things. And we'll talk a little bit more about what a bridle was. Literally, the electricians out of U.S. Steel was responsible for these things. And I was an electronic repairman, but these prints were so complicated for those guys that we would have to go down and troubleshoot, and then we would tell them which relay to replace. That's kind of and then they would replace it. We couldn't replace the relay, but we could troubleshoot it. Those guys were really, really good, but most of them came up through the apprenticeship program, and they literally carried a book in their back pocket. Did I tell you about that?
And every time something broke, they would write down what they did to fix it. And if it broke, if it did the same thing, they didn't know how to troubleshoot it. They knew how to look it up in their book. And they'd change that part out. And if it didn't fix it, they were what? That is lost. And they'd call us. They'll come down and troubleshoot this for us. So we'd come down there and troubleshoot it for them. We were responsible for all the thickness gauges, which were nothing but X-ray machines, and all the closed-circuit TVs, and all the motor drives, all the electronic drives down there. But those guys, and they were good. We didn't get called that much because usually when it broke, it was the same thing. But if it wasn't the same thing, those guys. But they didn't have any formal education. They came up through the ranks. So the electronic repairmen, they didn't have an apprenticeship program for the electronic repairmen. You had to have experience before you got there. This is what we call wire numbers. So every wire that is not connected to another wire gets a different number. If the wires are electrically the same, if they are connected together, they get the same number. Y'all understand that? So L1 gets that first number was labeled line number 1. And from then on, every wire that is connected to L1 gets the number what? 1. L2, as soon as I assign 3 to the L2, then every wire that is connected to L2 gets the same number. And people don't understand that. They say, I need to measure my lines. Well, they think by George they'd have to go all the way back to the power source to find the line. No, they didn't. All they had to find was line number 1 and line number 3. No matter where it's at in the whole system, they got a terminal board up there, and they see a 1 and a 3 by George. That's L1 and L2, and I can measure the voltage anywhere. In fact, when we wire these things up, we don't go back to the power source. We jump from device to device, just like the astronomer. You can't go back to the power source because if everyone went back to the power source, then I would try to hook 6 conductors under the same terminal block. Now legally, you can only, the maximum is 2. You can't, as soon as you put that 3, you're going to have problems. Over time, it's going to probably come loose. And why is that? Huh?
Wait.
Because of vibration and heat's the biggest problem. Because they get a little hot, they expand, they cool, they contract, and eventually they'll work themselves loose. Here we'll never. Here you cannot put more than 2 wires under the same terminal. Never. If you do it. So here's my L1. How many wires would we have there? We would have 1 wire going down here and connected to that switch. Then what I would do is I would put a wire that goes from here to here, here to here, here to here, right? There to there. And we do the same thing on L1. So no more than 2. So everything you should do, you should be able to do it with no more than 2 wires connected to any point. Okay, so how does the wire numbers go in between? So we start numbering. Now, why does this get a number? Why do we have a 1 there and we get a number there, a different number there? It's a different wire. It's not connected to another wire. So anytime you go through some type of device, it is going to get a different number. So there's a device right there. It's a what? It's a switch. As soon as it goes through that device, and this wire is not connected to that wire, then it gets a new number. So there's 1, 2, 3. Now, as soon as I sign the L2 number, then it is what? Everything that connects to L2 is going to get the same number. Then I come down here, I say 1. Why is this 1? Because all these wires are connected to L2, L1. Goes to this thing right here. Then it gets a what? 4, and then 3. Then we go 5. Why don't this guy right here have a number? It's part of 5. It's electrically the same. If you have wires that are connected together, you see that dot right there. That dot means those suckers are what? Connected, then they get the same number. And boy, when we all have to do this, y'all gonna be throwing numbers all over the place. Y'all gonna I have people number these things. They have to have numbers all over the place.
So the other side of that would be 1.
Other side of what?
The number 5.
When you say the other side, you mean the left-hand side?
The left-hand side.
Yeah, this will be 1. Why? Because all these are what? You see that dot right there? They're all connected together. If you see that dot, then everything connected to a dot will have the same number. This is electrically the same. This is electrically the same. All these are connected what? They are connected together. Everything that is connected together gets the same number. So over here, all these are connected together. So if I took an ohm meter and I put it way up here on L2, I remove power, and then I put it all the way around there, it's going to show me continuity. It's going to show me 0 ohms. Or way down in the tens. A lot of times a meter will measure the meter leads. So, but these two are connected together. How do I know they're connected together? That dot. So that means they get the same what? Number. So when I assign this 5 right here, we don't have to put 5 on there because I know it's what? It's 5. But if you want to, it's fine. So you won't get marked off if you come down here and put 5. I got the eraser out. If you come down here and put 5, and you don't have to circle, wire numbers are not circled. I don't know why they have them circled. Then that's fine if you want to do it, just to keep yourself from what? From screwing up. But if you come down and do this, mark that 6 and then go 7, 8, then you lose that one. But if you mark the rest of them in sequence, then you're not going to use a lot of points. If you mark everything, though, you're going to. And then this gets to number 3. We come over here, 1, 2, and this guy right here gives the people all kind of problems. Is this wire right here between the relay and the overlay? For some reason, people don't want to assign that thing a number. If it goes through something, and it's you see that line. You see that black thing right there? That is a line. That wire that represents a wire. Y'all understand? And we've gone through something. So if I've gone through something, it is not electrically connected here. So it is not electrically connected there because it would have a dot, right? You understand? Okay. And so it gets a what? It gets a number. 73189 So this is going to give people in this class problem. We got 14 people enrolled in this class, and I guarantee you, 5 people out of this class, probably more than that, is going to drop those numbers right there. And they'll put these numbers on terminal boards. They're either going to put wire numbers on them. So we have these. We can buy wire numbers, and they got adhesive on the end. They come in spools, and you can wrap the wire numbers around them. On the airplanes, all the wires on the airplane I worked on were white. And they literally burned the wire numbers into the jackets, and they put them every 6 inches. But everything you look in there, you'd have a bundle of wire, you know. If they took all the wires in the airplane I worked at and spread it out, it'd probably go around the earth. I mean, it was a lot of wire. You'd see wires, you know, that big, and they didn't use cable, they used individual wires. And then they were wire tied together. But they don't use the plastic wire, they use the plastic wire ties, they use the wax string. It was beautiful. Learning how to run that wax string. But usually at a big plant, like a commercial plant, they don't put any numbers on any wires. They number the terminals that these things go to. Y'all know terminals, right? So they'll go to a terminal strip, and then the numbers will be on the terminal strip. You get into a big plant like US Steel, all the wires are black. They run black. Because that way they can buy the wires in gross, right? You understand? They don't have to buy, okay, we run 3-phase, it's supposed to be red, blue, green. They don't do that garbage. They run all the same color wire. The only time you'll see different color wire at a plant like that is if they pull a cable. And, so a lot of your signals come through cables, but when you get into these control circuits, they're all usually all one color. And industry likes to use what? Black. Luckily, your car don't use wire numbers. What does your car use? It uses color codes. So they got thousands of color codes. And every time it goes through a connector, follow it out. You'll see it comes in here, it might be green and red stripe, and you come over here on the other side of the connector, it'll have a different color code. Because it goes to a different connector. So cars, they don't use wire numbers, but they use a color code to identify the wires. Go out there and look at your wire numbers sometimes, you can see those wires that I showed you. And so when you buy the prints, that's what it does, it gives you colors. I can show you the print on my HHR. I had all the speakers in my HHR stop working. Every one of them. And every speaker was bad. So, trying to figure out, I thought it had an open, but trying to figure out those was neat. Okay. We're not going to use very many wire numbers, but I go back and look at my US Steel print. So what we're doing is we're coming from what the book says it does, and then we're looking at true ladder diagrams from a company, right? You understand? Following the industry standards. If they don't follow industry standards, you'd probably cry. So here they are, line numbers. Here they're up to 137,000. So notice what they're doing here is they're starting the first 3 digits of the wire number actually identifies the page of the diagram it's on. So 137,000. So that don't mean we got 137,000 wires. It's just that this is the way they came up with the wire numbers, right? So the first digit is the what? The page. And then now they're already up to line 12, or wire number 12, which has nothing to do with wire number. Line number. And notice, every time it goes through something, so look, down here they put 137011. This guy here has no number. Why don't they have a number? Because it is still 137011. It's just that they don't clutter the prints with a bunch of wire numbers. So every one down this line would be 137011. As soon as it comes through there, it gets another number, and it might not be consecutive. But it's going to be another number, right? You understand? So this jumps to 137014. Why did they do that? I don't know how they did that. It's just that's the reason they came up with. This might have been the 3rd revision of the print, and every time they just signed a different number. So this number right here is 137014. This is 137012. So it looks like this guy right here was what? It was added. But they had already assigned this wire the 12. So when they got out here, they came back and added it, and then they came up here and gave it a different number. Now so why don't we have a wire number all down here? So all these wire numbers are what? 137012. Because they are connected together. How do I know they are connected together? The dot. And this is US Steel. This is a true diagram. This is a wiring diagram out of a true plant. Number 4 galvanized line. Which I learned and cried a little bit after we shut down. I spent a lot of time in there. That was one of the cleanest plants in US Steel. They galvanized, they put the zinc coating. I hope y'all familiar with the galvanized metal, right? They were the ones that put the zinc coating on the tin. And it was a neat place. Had a bunch of radio controlled cranes down there that we worked on. Nice FCR drives that were really neat. And it was real neat because it was a continuous strip furnace, mill, and they could stop the feeding in, and they could stop the takeoff in, and never stop the center. They couldn't stop the center because it was running through a furnace. They had to preheat it, so they had to get it up to the right temperature so the zinc would adhere to the metal. If you stopped it inside the furnace, that's what would happen to the strip. It melted in two. Okay, the next thing is not going to be on our UL steel print, but this is what we're going to use. That's these guys right here. These are called manufacturer numbers. And basically, this shows us how to connect to different devices. So where's our motor start? Did I pass it? What did I do? Huh? No, that's a push button.
That's pretty good.
I had the motor started. That black panel showed it to you. I passed it.
Oh, he put the pound back.
Oh, or somebody did that. The last person, thank you. So what you get usually when you buy these devices, you get a little slip of paper. And then what they do, assign every terminal, they assign it a number, which is real hard to see on here. Okay. But what they do, they assign every terminal a number. So can you see that? So that would be terminal 2. They're calling this L1, L2, L3. And then we have terminal numbers. Can y'all see these? And then what they do on our panels is they give us an additional little layout of the relay itself. Okay. So this guy here has 6 contacts on it. But up above this are these little numbers. These are called manufacturer numbers. And now what we've done is we've come back and we've transposed up here on our terminal board, we transferred the true manufacturer number. So these are the manufacturer's numbers. So this would be terminal number 5. That makes sense? And then I can come up here and look at this diagram as soon as I get my sides right. And I could find the terminal 5. So there's terminal 5 right there. I think. I can't see, I got my glasses on. Yeah. So that means and this is a normally open contact that's between numbers 5 and 6. So if I wanted to use that contact, then I would bring in a wire into number 5, and then my other wire would come out of 6. So what does the manufacturer numbers do? They show you actually how to connect the terminals on the device itself. Has nothing to do with wire numbers. When Cutler Hammer is a really big manufacturer of control devices, by the way. You'll run into a lot of Cutler Hammer relays out there. When Cutler Hammer had put out this device, they put it out for everybody, right? And they had no idea whether U.S. Steel was going to buy it or whether we at Lawson State was going to buy this thing. So they have no idea about the wire numbers. So what they do is they provide a section of numbers that tells me where to hook my wire numbers to, right? You understand? So I know if I want to hook it to number 5, then I need to have this little diagram that shows me what number 5 actually goes to. So I need a normally open contact. So I come over here and I start looking for normally open contact on this guy right here. And then I say, okay, here's a normally open right here. These are your power contacts, by the way. So we wouldn't use, okay, and there's our overloads, which are part of, here's the overloads down here. There's the reset switch. Okay. But if I looked at the device itself, I would find these numbers up on the device itself. So all we've done is transpose these what? These manufacturer numbers down to these terminal blocks. You okay? So when you wire a circuit, what you're going to have to do is we're not going to use wire numbers in this class because we don't have enough wires to fool around with using wire numbers. And plus we don't have the ability to put wire numbers on the wire anyway. But you are going to have to write manufacturer numbers. So what you're going to do on your prints, before you wire them up, you're going to look at all your devices, you're going to assign these manufacturer numbers. And then what you have to do, you can say, okay, hook this from L1 to number 1 on this relay. Or hook it from number 1 to number something on the light bulb, right? You understand? So if you come up here and look at all the devices, what we have is we have the terminal boards have these manufacturer numbers on them. And the manufacturer numbers is what we use to wire these devices up. So here's the device. This will be drawn somewhere either on the device itself. So a lot of these little control relays, they'll actually have the layup and the manufacturer numbers on the little plastic cap that covers that. Normally, if you buy a big relay, you come with a little slip of paper that has that. Normally, what you can do, if you got it out, you can figure out the contacts in the relay with an ohm meter if you don't have the little sheet on there. But when you're figuring out your contacts, you need to manually push the thing in or let it open so you can find it normally open and on the code. So you're going to be required to do that. If I come back there and you got something wired up, it would be almost impossible for me to try to figure out how you got it wired up, unless you got what? The manufacturer's number. Now I can look and see a wire that's supposed to go between 6 on this to 4 on this, right? You understand? And it makes it real fast for us to. Also, it helps you troubleshoot. So assign manufacturer numbers. And where do you get the manufacturer numbers at? Off the device you chose to use, right? So we're not going to do wire numbers. You'll have to assign wire numbers. So on the test, by the way, wire numbers, contact, cross-reference numbers, and line numbers, big things. And we'll probably see that on every test. Hopefully by the time it gets on the final exam, the people that just throw numbers up there will finally be able to do it. I've seen people just throw numbers all over the place. Is anybody in this class going to do that? If everybody gets those things right on the test, which we have a test coming up next week, right? If everybody gets those right on the test, then it'll be the first class I've ever taught. This is usually a pretty good size class. We usually end up 14 people. 14 is all we allow in this class. Sometimes we come up, so normally when we do, see this dash line right here? This is it. We're going to dismiss. But remember, the ELT 209 people, you have to give the class at least 3 hours before Thursday, right? Because I have to turn my bow in on Friday morning, the chemistry test. If you see this little dash line between 2 control devices, or between 2 devices, it means they are mechanically interlocked together. So that would be the same limit switch. So the first 2 in line 1 and line 2 on the top ladder diagram, that dash line means they are what? Mechanically connected together. Now the problem is that little dash line works out great if the 2 devices are in consecutive line numbers. But those 2 devices that are mechanically connected do not have to be in consecutive line numbers. So they had to come up with a device where we couldn't put those things in consecutive line, put the control device in consecutive line numbers. So notice what they've done. So here in line 1, I have a pressure switch. Now these 2 pressure switches are together. They're in the same unit. They are the same unit. It's just that pressure sensor, it opens and normally closes, and also closes and normally open, right? You understand? But we couldn't put them in consecutive line numbers. So what did they do? Well, they put this little house up there. They put a number inside of it. But that house has a pointing in, right, like an arrow. And it's pointing down. So I start following that down. This is number what? 5. And then I see this guy down here. So number 5, what's it telling me? Look at, not line 5. Line 5. You're going to have to get out of that habit. Even though it does work out the same. In motor controls, rungs do not have numbers. When you take PLC, the rungs are numbered. So you start a new run, and all the runs are numbered. In motor control, runs are not numbered. What's numbered? So this is telling me I need to look for its brother down in line 5. And then when I get down to line 5, I see the same old thing. It says this brother's up in line 1. And it means these two devices here are mechanically interconnected. But if I came up here and started drawing that dashed line, then that's going to give us problems, right? Because now that dashed line would have to go through other lines, and that would cause a lot of confusion. So now I would think the thermal switch was connected, but it's not, right? You understand? So these little houses, or arrows, are a technique that we use to indicate we have a mechanical interlock when devices that are not located in consecutive lines. Okay, guys, so what are y'all going to bring in Thursday? You need to try bringing your lab book, right? And we'll finish up this chapter. We'll talk about the lab procedures. We'll talk about how the lab book is laid out. And bring in your safety glasses. You're required to have your safety glasses on anytime you get up here, right? Understand that. Bring in your safety glasses. ELT 209, you got to make 3 hours up. You can do it today, you can do it tomorrow, but you got to make it up in the library. And you got 7 additional assignments that you're supposed to submit before the term's up.
We have the topic quiz due in this class. We don't have a topic quiz due in digital yet, do we?
No, we
Just
haven't
the
finished the
worksheet.
chapter. We haven't finished the chapter.
Yeah, we just got to bring that worksheet in tomorrow. Okay, I'll just make it sure.
Just been.
Doing this house, do I have this library? I got to keep this house. Or do I have
No, you got to do it here.
Okay.
Because I have to document you here.
Oh,
I can't take, because you have to give, the contact the credit, you physically have to be on campus those additional hours. So if you do it in the college library, even if you bring your computer, we have free internet here, if you rather use your computer than use the one downstairs, that's fine. You just have to do it at the library. But you can do it on this campus or you can do it on Birmingham campus. But when you go in the library, you have to swipe your card. And then what they do is they run that for me and they show me the hours you're in. And I wish you could do it at home, but that's not the way that contact credit works. You have to be on campus those additional.
so it wouldn't matter which campus I go to. Okay.
Just go into the library, Birmingham campus, and find Birmingham classes over there. So it'd be more, yeah. So when you go into either library, you got to swipe your card, and then computer services sends me that thing every Friday morning. So
Call. I do like
you got any student ID? You have a student ID card yet? You know where the bookstore is on this campus? There's a little room over there. Just tell one of those ladies you need a student ID, and they can do it on this campus. Where they do the student IDs in the Birmingham campus, I have no idea. They don't teach over there. Yeah, just go down to the bookstore here on this campus. Go up to the lane, and it's the little room beside, the police have it's a little room over to.
right possible. Right
No, it's right beside it.
Okay.
I mean, there's a restroom, there's a generic restroom on one end, there's a little old room on the other side, and that's where they do student IDs at. Yeah, probably will still be doing it. Or they'll get somebody that can do it for you. You gotta have that student ID. Because if you go to the library, they won't even let you in.
Without ID. And all my signs are there on this blackboard.
Yeah, inside the assignment section.
Okay.
So the blackboard, you haven't used Blackboard before?
No, but my girlfriend, she knows how to use it.
Okay. But your username is, your username should be the part of your name up there. Yeah, but without the app.
Oh, without the app.
Yeah, so that's your username. And then your home password is your birthday. I'll tell you right now.